Hello, and welcome to Linear Algebra. This is lecture 11. Today we'll be talking about the LU decomposition. Right, so last time we noticed that given any m by n matrix, there is a matrix B of the same size in reduced row echelon form, and there are elementary matrices. I remember an elementary matrix is one that is obtained from the identity matrix by performing a single row operation. E1 through Ek, size m by m, such that A is E1 Ek times B. Right, so you can always relate a matrix and that matrix in reduced row echelon form by multiplication with elementary matrices. We also learned that A is invertible if and only if its reduced row echelon form is equal to the identity, and in that case, the reduced row echelon form of the identity, if the matrix A augmented with the identity matrix is equal to the identity matrix augmented with A inverse. Right, so that gave us a way of finding inverses of matrices. Okay, this time we're going to talk about the LU decomposition. Right, so we're still very much on the topic of solving systems of linear equations, but this time we're going to do it by breaking the matrix up into two pieces. So here L stands for lower triangular, for a lower triangular matrix, and U stands for an upper triangular matrix, right? So this means basically what you would think. Lower triangular means something like this, and upper triangular means something like this. But let's be precise. So a matrix A, notice it doesn't have to be square, is lower triangular if Aij is equal to 0 whenever I is less than j. So for example, A0, 0, B, C, D, E, F, 0. That is a lower triangular 3 by 3 matrix. Matrix A of size m by n is upper triangular if Aij is equal to 0 whenever j is greater than 1. So for example, A, B, C, D, E, F, like that, that's upper triangular. One thing to notice is that we put no condition on these coefficients or these coefficients. For example, the 0 matrix or a diagonal matrix counts as both lower triangular and upper triangular. Okay, here's another example. The elementary matrix PCIA, IJ from last time, Right, remember this carries out the first type of row operation where you add a multiple of, in this case, the multiple C times row J to row I. Right, so this is lower triangular if I is less than J, and upper triangular if I is greater than J. So, for example, P531, right, which was the example we saw last time, right, this is lower triangular, right, with, I think I might have written that backwards. This is lower triangular, and I is bigger. Yes, these are backwards. Sorry about that. If I is greater than J, if I is less than J. Okay. As we see clearly from this example. And similarly, P513, 105, 0, 1, 0, 0, 0, 1. This is upper triangular, and we have I less than J. Okay. Okay, so now say we're given a matrix. Let's say 3 by 3. And let's denote its entries like this. And we wanted to use row operations to make it upper triangular. That is, to get D equal to G equal to H equal to 0, right? So to make this upper triangular, we don't care what those coefficients are, but we need these to be 0. Right? Then in the simplest case, right? So assume the odds are in our favor and we never have to worry about getting a pivot where we need it, then we would only use, need to use row operation R1 repeatedly. And add a multiple of a row to a lower row. Right? So what do I mean by the simplest case? Well, what you'd want to do to start with is, let's get rid of this D and this G using A, right? So as long as A is not 0, I can add a multiple of this row to this one and get rid of D and G, right? Make them 0, right? Now, when I've done that, I've changed E, assuming D was not already 0. I've changed E, but if we're lucky, when we've gotten to this step, E is not 0. And so then we can use it to add a multiple of this row to this row and get rid of H, make it 0, right? So in the simplest case, we have pivots when we need them, and just doing row operation R1 repeatedly from one row to a lower row gets us to upper triangular. So in that case, we would have P, C, K, I, K, J, K, to P, C1, I1, J1 times A equal to U, right? And in each of these, we're doing a a row operation where you're adding one row to a lower row, right? So that's of this form. So I would always be greater than j. So IL greater than JL for every L. And then we can solve for A. So solving for A, we find that A is equal to P, C, K, I, K, J, K, dot, 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 P, C1, I1, J1, all of that inverse times U, right, which we can write as, remember the inverse is, so two things. The inverse of a product is the product of the inverses in the opposite order, and the inverse of an elementary matrix of type P is another elementary matrix of type P. You just change the sign of the constant. Sorry, this would be 1. CK minus CK. IK, JK. Times U. Right? And now this, each of these matrices is lower triangular, and it's an exercise to show that the product of lower triangular matrices is again lower triangular. So I can denote this matrix as L, and notice that I've written A as the product of a lower triangular and an upper triangular, just like we wanted. Right? Okay, so let's write this down as an algorithm for finding the LU decomposition of a matrix. In fact, this algorithm also will tell you whether or not there is an LU decomposition, because there might not be. Okay, so step 1, try to reduce A to an upper triangular matrix using only row operations of type R1 and only ever adding a multiple of row j to row I if I is greater than j. If this succeeds, call the result U. If it fails, then A does not have an LU decomposition. Right? How do we know that? Well, you can always write the inverse of this, if you have such a thing. And without loss of generality, you can assume that L has 1s on the diagonal. Then you can find its inverse using elementary matrices of exactly this type. And so multiplying A by the inverse would carry out these row operations and obtain U. Right? So if you have an LU decomposition, it has to be, U has to be obtained from A in this way. Okay, and then step 2, if the previous step succeeded, then define L, M by M, F to be the lower triangular matrix with ones on the diagonal, and minus C in the ijth entry if during the elimination process C times row J was added to row I. Then A is equal to L times U. Okay, so that's the algorithm. Let's do an example. Find the LU decomposition. If it exists, of the matrix A, 3, minus 9, 15, 3, 1, minus 1, 9, 9, minus 5, 14, minus 23, minus 9, 2, minus 5, 12, 7, 0, minus 1, 2, 1. Okay, great. So we know what to do. We're going to start with this matrix and perform row operations. Okay, so we want to perform row operations and end up upper triangular, right? So here, that means that everything below that line has to be 0. So we need this 0 and all of these 0. Okay. Okay. So what we do is I'm going to so over here I'm going to keep track of what. Here, let me put ones on the diagonal. Here we're going to be constructing L. Okay, so nothing's going to happen to the first row. Now, I want to get rid of this 9, right? To get rid of the 9, I'm going to add a multiple of this row. So I multiply this row by 3 and then add it to this one, right? So what am I going to get? Here I get 0, then I get 2 minus 1, 1 minus 1, right? Okay, but now since I did that, I did 3 times this row and I added to this one. So here I'm going to put a minus 3. Okay, next, this row, right? I want to get rid of the 15. So what I'm going to do is multiply this row by minus 5 and add it to this one. Okay, so I do that. I end up with 0, 4, 2, 2, 2. Okay, now I'm going to, in constructing L, I'm going to figure out what goes here. So what did I do? I did this one, multiplied it by 5, minus 5, and added it to this one. So that means here I put a positive 5. Okay, same thing. Here I want to get rid of this 3. So I'm going to multiply this row by minus 1 and add it to that one. So I get 0, 8, minus 4, 5, 1. Okay, and so I did this time, this one times minus 1 and added it to this one. That means that here I'm going to put a 1. Okay, excellent. So now I'm happy with the first column. So now I'm going to go with the second column. And fortunately, I still have a non-zero entry here. So my pivot is on the diagonal. I can use that to clean up its column. Okay, so nothing is going to happen to the first row, and nothing is going to happen to the second row. Now, and nothing's going to happen in the first column because those are all zeros. So now I'm going to use this 2 to get rid of this 4. So what I'm going to do is take this row, multiply it by -2, and add it to this one. Right? So I'm going to get 0, 4, 0, 4. And because I multiplied it by -2 and added, that means that in this spot of this matrix, I should put a 2. Okay, and then next I look at this 8, and I'm going to get rid of it using this 2. So what I'm going to do is multiply this row by -4 and add it to this one. Right, and so I get zeros, 1, 5. Okay, and so over here, I'm going to put a +4. Okay, so now let's stare at the matrix that we have here. There's the diagonal, and below the diagonal, I have zeros. So I'm done. This is the matrix U. Right, and we can write how we got U in terms of A. So U is, so to A, the first thing we did was P3, 2, 1. Then the next thing we did was P -5, 3, 1. Then the next thing we did was P -1, 4, 1. Then we did P -2, 3, 2. And then P -4, 4, 2. Okay, so hence A is equal to P -3, 2, 1, P 5, 3, 1, P 2, 3, 2, P 4, 4, 2 times U, and this altogether is L. And notice that this is exactly the matrix that we have over here that we were building while we were doing this process. And that's how you do it in practice, that you construct the matrix L while you're constructing the matrix U. So this matrix L that we have here, this is just all of the steps that we had to do. So everywhere else, I should just put zeros. And this is indeed the same matrix L as this product. Right? So we could write our conclusion that A is equal to this matrix L, 1, -3, 5, 1, 0, 1, 2, 4, 0, 0, 1, 0, 0, 0, 0, 1, times this matrix U, 3, 0, 0, 0, 1, 2, 0, 0, -5, -1, 4, 0, 2, 1, 0, 1, 0, -1, 4, 5. Okay, now you might be wondering, why? Why would you want to do this? Well, it has to do with solving systems of linear equations. Let's say that I have a decomposition of A into a lower triangular and an upper triangular. Then to solve AX equal to B, well, AX equal to B is the same as LUX equal to B. So we solve this by setting Y equal to U times X, so that L times Y is equal to B. Vectors. And the point is that triangular systems are easy. They're easy and they're fast. So it is easy to solve Ly equal to B. And once we know Y, then it is easy to solve Ux equal to Y to find X. Okay, now I'll say this is usually the preferred method for solving linear systems. Okay, by that I mean that often when a computer is solving a linear system, this is what it's doing. It's doing the LU decomposition. Now, on the one hand, LU decomposition is really the same thing as Gaussian elimination, because we're finding L and U by doing row operations, right? And Gaussian elimination, you do row operations. So two things. So first, I'm going to do an example to show you how easy it is to solve these systems. But first, let me tell you, like, why would you want to do this instead of just doing Gaussian elimination when we've been doing Gaussian elimination? And the answer is that this is like doing the row operations just once. You do them once to find L and U starting from A. And now, every time I give you a B, you can solve AX equal to B using the matrices L and U. And so these two quick and easy systems. So this is a really good idea if you're in a situation where you want to solve AX equal to B many times with many different B's. Right? Now, you could say, well, we saw in a previous lecture that I can do that all at the same time. If you give me B1 and B2, it's fine. I'll just take the augmented matrix with A on the left and then B1 and B2 on the right, just do Gaussian elimination once, and I've solved both systems at the same time. That's true. That's true. You're right. But what if when you have B1, you don't have B2 yet? Right? So, for example, many optimization algorithms require solving a linear equation to make each step. So, as I mentioned in the first lecture, we care a lot about linear algebra because even when you're doing something non-linear, the way you do it is you approximate it by something linear because that's much easier to understand. So for example, it can happen when you're solving a nonlinear equation or when you're doing some sort of optimization algorithm that you'll solve it by taking lots of steps, and each step gets you closer to the true solution. And each step is done linearly, solving a linear system of equations. Right? So A will come from linearizing something, the function you're interested in, or something coming from the algorithm. But B, to know which step to take, you have to know what steps you've taken before. So you don't know B2 until you know B1, and you don't know B3 until you know B1 and B2, and so on. So in that sort of situation, you know you're going to be solving AX equal to B lots of times, but you don't know the right-hand sides yet. So if you can do this to make it quick to solve AX equal to B, no matter what B you're given, then you're in good shape. Okay, so now let me try to justify that you are in good shape, that it's easy to solve these. So let's do an example. Let's use the same matrix A as above because we've already found its LU decomposition. And let's say we want to solve A times X is equal to B, where B is the vector 4, minus 10, 20, 13. Okay, so here, let me copy these matrices. Let me just copy this. Okay, so first, we find the unique solution to Ly equal to B Okay, so this, again, this is easy. So how do we do this? So Ly equal to B. So let's say I just translate this into a system of equations, right? So this would say y1, right? So I'm using these rows. This is my coefficient matrix. So y1 equals 4, then minus 3y1 plus y2 is equal to minus 10. Then 5y1 plus 2y2 plus y3 is equal to 20. And then y1 plus 4y2 plus y4 is equal to 13. Right, so I'm getting the right-hand side from here. Okay, now, since you have ones on the diagonal, then this equation tells me what the value of y1. In this equation, I'll figure out y2 because I already know y1. In this equation, I'll figure out y3 because I already know y2 and y1. And in this equation, I'll figure out y4 because I already know y2 and y1. Right? So every step, you're figuring out the value of yk because you already know the previous values of y, and that's all that can show up because it's lower triangular. So in particular, in this case, we can just read off here, y1 is equal to 4, y2 is equal to 2, y3 is equal to -4, and y4 is equal to 1. Okay, next we solve ux is equal to y. Okay, now when we're using L, we're guaranteed that there's a unique solution. The ones on the diagonal guarantee that. Excuse me. In the case of U is in reduced row echelon form, but there's no, it's not reduced. It's in, it doesn't have ones on the diagonal, right? But otherwise, it is in echelons. So we have pivots here, but this one does not have a pivot. So this is going to be a free variable. x5 is a free variable. So next we solve this, say, with x5 as a free variable. Okay, so let's just translate this into a system. Right? So this is 3x1 plus x2 minus 5x3 plus 2x4 is equal to what? 4. Right? So now my right-hand side is going to be over here, like ux equal to y. Then the second equation says 2x2 minus x3 plus x4 minus x5 is equal to 2. Then the next equation says 4x3 plus 4x5 is equal to -4. And then the final one says x4 plus 5x5 is equal to 1. Okay, so now to go from here to here is known as forward substitution because I know y1, then I know y2, then I know y3, then I know y4. What we're going to do here, because it's upper triangular, is known as backward substitution. So from here, so remember x5 is a free variable, so we're trying to figure out everybody else in terms of x5. From here, we know x4. Since we already know x4, it doesn't even show up here, but then here we know x3. Since we already know x3 and x4, then from this equation, we know x2. And since we know x2, x3, x4, from this equation, we know x1. Right? So let's do that. So here I know that x4 is equal to 1 minus 5x5. From here, I know that x3 is equal to -1 minus x5. From here, then I know that x2 is equal to 5/2 of x5. And then from here, I know that x1 is equal to -1 plus 5/6 x5. Right? And there we go. This is the solution to the original system, ax equal to b. Right? x5 is a real variable. Sorry, it's a free variable, so it's allowed to be any real number. So we could say here, so the set of solutions of ax equal to b is, you have the x1 is -1. So I'm going to put the constants here. So I'll get -1, 0, -1, 1, 0. And then I'll put the x5. I'm just going to write it as t because it's a parameter. So I can use any letter to denote it. So it's t times 5/6 for x1, 5/2 for x2, minus 1 for x3, minus 5 for x4, and then just 1 for x5. And here t is allowed to be any real number. Okay, so you see that if you have an LU decomposition, then it's very quick to solve ax equal to b, because you just do forward substitution to find y, and then backward substitution to find x. Okay, now I've mentioned that not every matrix has an LU decomposition. So let's see an example of that. Sometimes a matrix does not have an LU decomposition. For example, consider the matrix 0, 1, 1, 0. Right? And let's say that I try to write it as a lower triangular times an upper triangular. Right? So, and here, let's not even impose that the lower triangular matrix have ones on the diagonal. Let's just try the most general lower triangular times the most general upper triangular. Okay. Well, if you write out this product, you get L1 U1, L2 times U1, then L1 times U2, and then L2 U2 plus L3 U3. Okay, so if this matrix is equal to this matrix, then notice, so here, let's put a question mark here because we're going to see that this is impossible. So here we would need, so on the one hand, 0 is equal to L1 U1, but 1 is equal to L1 U2 and to L2 U1. And notice the problem. If L1 times U1 is equal to 0, then either L1 is 0 or U1 is 0. But if L1 is equal to 0, then L1 U2 has to be 0. So that won't work. And if U1 is equal to 0, then L2 U1 has to be equal to 0. So that won't work. So it's impossible to have write this matrix as a product of a lower triangular and an upper triangular. There is a fix. So in this case, however, it's really easy to see how you would get this to be upper triangular. You would just switch the order of the rows, right? So, and it turns out that that's all you need to do. If we allow ourselves to switch the order of the rows first, then we can always find an LU decomposition. So let's state that as a theorem. For every matrix A, size m by n, there is a matrix P, P for permutation, which is a product of elementary matrices of the form Rij, so just switching rows. Right, so there's a matrix P, there is a matrix, an upper triangular matrix, U, same size as A, and a lower triangular, L, of size m by m such that P times A is equal to L times U. So as long as you're allowed to switch the order of the rows of A, then the matrix you end up with does have an LU decomposition. So this is the LU with pivoting decomposition of A. Okay, so let's check that this is true. Well, any matrix can be put into upper triangular form by using row operations of type 1 and 3. So type R1 and R3. All right, so remember when we were thinking about whether or not the odds were in our favor, the question was just, do you have a pivot on the diagonal when you need one? But if you're allowed to switch rows, then if you need that pivot on the diagonal, that means that there is something in that column below it, below the diagonal, right? And so if you don't have a pivot on the diagonal, then you can always switch rows to put that non-zero entry, one of the non-zero entries from that column on the diagonal without messing anything up in any previous column. And so then you can continue the algorithm. So if you're allowed to use operations for R1 and R1 and R3, then you can always get to upper triangular. Now the question is, can you do all of the row switching first and then use all of the R1 operations with always just going down? So all we need to check is that it is possible to carry out the row exchanges first, and then the row operations of type 1. Okay, but this follows from, so let's say that you did a row operation after you did a operation of type R1. So in terms of elementary matrices, it means that first you multiply it by P and then you multiply it by R, right? I want to check that you could have done things in the opposite order. Maybe not using the same matrices, but still row operations of type R1 and R3. So there are several cases, but you can see that, well, the simplest case is if I, J, K, and L are completely different, then these two operations just commute. On the other hand, you get P, C, J, L, R, J, K. If I is equal to K and J is not equal to L, you get P, C, K, J, R, L, J. If I is equal to L and J is not equal to K. And then finally you get P, C, L, K, R, K, L. If I is equal to K and J is equal to L. And I'll let you check these, of course, very quick and easy to check. But notice that in every case, you end up with P before R. Okay, and that's all we need to check. Perfect. So we will stop there for today and pick it up there next time.